Good morning, everyone. So in the last class, we have seen how to do very simple code generation, and we will continue further in seeing how we can take the generated code and apply some simple register allocation algorithms on that code. So for the simple code generation module that we have seen, so the input to the code generation module, it's a program in three address form. So the program is a sequence of three address tuples, and the code generation module, it generates target machine code. But the primary thing is instead of the target machine code will can contain some physical registers and large number of virtual registers. And these virtual registers, they don't have physical realization on the processor as their name indicates. So in order for us to be able to execute that code on the target machine, we have to map these virtual registers to physical registers. Just to recap the simple code generation algorithm that we followed. So what we do is we construct a control flow graph representation for the sequence of three address tuples we have. And then by looking at the control flow graph, we can do pointer analysis and other analysis algorithms we can perform on the CFG. And so, of course, this the CFG that we have in hand, it's an optimized CFG. Before we do this code generation, we would have applied multiple optimizations on the CFG. So now we have a CFG with three address tuples in the basic blocks, and we may have to do one more analysis pass to figure out which variables can safely reside in the registers. And all the variables which can safely reside in registers, we assign them virtual registers. And all the variables which cannot safely reside in registers, we retain them in the memory. And when we generate code, uh, we keep this in mind, that whether the variable that we are accessing, if it is register safe, or it is residing in the memory. So that's step 3. So we make a pass over the CFG, generating assembly code, assuming that the target machine contains infinitely many registers. We call them as virtual registers. And then we apply a register allocation algorithm on this IR, which is very close to the target assembly code. And finally, after register allocation is done, we generate code with the actual registers in place. So this is the process. Just to recap our discussion from the last class. So let's say if there are three variables x, y, z, and the tuple that we have is x is equal to, let's say we are assuming that the tuple we have is x is equal to y plus z. And all of them, they are register safe. They are allocated registers, virtual registers, VRI, VRG, and VRK. Then the code that we generate, then if it's a risk instruction set architecture, would be something like this. And even for CISC instruction set architecture, in this particular case, the code, the generated code looks very similar. And there is an assumption when that these registers, these variables x, y, z are already promoted from memory to virtual registers, and corresponding to that promotion, we would have generated code somewhere ahead. So assuming that, because otherwise if you are accessing the variables x, y, and z for the first time, especially the variables y and z, if you are accessing them for the first time, we may have to generate extra code to load the contents of those variables into the virtual registers VRG and VRK respectively. We are assuming that that code is already generated, variables Y and Z are already promoted to the registers VRG and VRK respectively. And second case is if Y is a local variable, uh, that is, it's not register safe, so it's a local variable. Then what we do is we use the scratchpad register RT to move the contents of, to load the contents of variable Y into register RT. And then we perform the arithmetic operation and the result stays in VRI. This is the case in the RISC code. In the RISC instruction set architectures, they are what are called as load store architectures. That is, the operands on which the computations have to happen, they have to be present in the registers only, all the three operands. That is a typical property of RISC instruction set architectures. But whereas in the CISC instruction set architectures, one of the operands can be present in the memory. It's not an issue. So here, since uh, the variable Z is in a virtual register, so when we generate code for the CISC instruction set architecture, we can just get away by using one instruction. So VRK stands as it is, and the second operand is the second source operand, that is Y. It is coming from the memory, and the destination is present in virtual register VRI. So this gives the big picture, and let's take a look at the last case where all the variables X, Y, Z, they are not register safe. In which case, in the case of RISC instruction set architecture, we are loading so this is an instruction to move the contents of register the variable Y, to load the contents of variable Y into a scratchpad register RT. And the second load instruction moves the contents of variable Z into a scratchpad register RU. And RS is a scratchpad register again to store intermediate values computed. So RT and RU are added and they will be stored in register RS. And the contents of register RS will be moved or stored into the memory location associated with variable X. And if you see in the case of RISC, so one of the operands Y is promoted to the scratchpad register RT, and the second operand we are just keeping it in the memory because we don't need to promote it, because for the add instruction one of the operands can come from the memory, and the destination is stored in the scratchpad. The value computed is stored in the scratchpad register RS, and RS is moved. The contents of RS is moved or stored into the memory associated with variable X. So as you can see, in the third case where all the variables have to be present in the memory, this is what is called as a compute intensity of the program will be extremely bad. So if you think about it, compute intensity, the number of computations done unit uh, per unit amount of data. Like for example, if you see compute intensity, let's call as compute intensity. Computations per unit data fetched. So here, if you look at the compute intensity, let's use the shorthand CI for it. So compute intensity CI. So we are doing one computation for 3 memory. It's rather than per unit data fetched, we may want to say per unit memory access, computations per memory access, if let's call it that way. So what happens here is, so we are making 3 memory accesses, but we are doing one computation. So the compute intensity is extremely bad. But whereas if you see the compute intensity when all the variables are promoted to registers, it is extremely good. Okay, so and this is what we would like to have. We would like to have. Our goal in the code generation and register allocation in general in the backend of the compiler is to generate code in such a way the number of times the processor has to go to main memory and fetch the data, it gets minimized. And if you actually think about it, so like there is the CPU and then there is a cache. So there is an on-chip cache and there's an off-chip cache. So there will be optimizations that will be done to see that no. So you try to keep data in the registers, and also you want to generate code in such a way you use the cache also well. Let's for the sake of simplicity, let's assume there is only on-chip cache CPU, and CPU has registers, and then you have memory. And the speed at which your processor executes and the speed at which your memory can supply data to the CPU, there is a huge mismatch. So memory is usually the bottleneck. So when we do code generation, our effort is to see that we use the registers on the CPU, that we use the available cache in such a way so that we can minimize the number of times we go and visit the main memory, because main memory is a bottleneck. In other words, we want to maximize the compute intensity. We want to maximize the compute intensity. So this is a very important goal. So before we move further, I want you to make a note of these registers: stack pointer, base pointer, registers RS, RT, RU, and there will be some other special purpose registers also. All these registers, they will not be used in the register allocation algorithm, because registers such as SP and BP, they have a special purpose. We cannot allocate them to any virtual registers. We cannot map any virtual registers to them. And few registers like RS, RT, RU, they have to be kept as scratchpad registers to take care of cases such as what we have seen just now. Okay, so few scratchpad registers and special purpose registers, we have to keep them aside. So if you look at the backend, so in the backend usually consists of, we take the IR and that is sequence of 3 address tuples, and we have to use suitable instructions to map this IR into target machine code. And so uh, what we have seen is a very naive method. That is, if there is an addition operation, use add. If it is mul, you may want to use mul, but you can be more sophisticated in your instruction selection. Like for example, when you are multiplying something by 2, instead of using a multiply instruction, you can possibly use a shift instruction to get the same job done. Yesterday, in the last session, Professor Uday is talking about much of backend in the modern compilers being automated uh, is like this. Because we can easily provide, when we want to generate code generation, large part of the backend can be automated uh, by kind of saying, if you see this operation and the IR, you just use these instructions. If you provide such kind of mapping from the operations that you see in IR to the instructions that are present in the target assembly code, then this instruction selection and code generation can automatically happen. That is, you don't explicitly need to write a code generation algorithm. All you can do is you kind of provide a table which maps the IR operations to the target machine code. So part of the backend can be retargeted, can be automated. Just like the way we do know, like in the parser generation, we specify the grammar and the parser gets generated. In the backend also, it is possible to kind of provide some metadata to the uh, code generator, and most things will happen automatically. And you can also specify these are the registers available, these are the scratchpad registers, these are the special purpose registers, and the stack pointer register in this architecture is called as SP, things like that. So after this is done, so this is the code generation, we do register allocation. And after register allocation, so there is a phase called as instruction scheduling. And so instruction scheduling we will not see in this class, but broadly speaking, so like for example, if you have an instruction like this, multiply R1, R2, R3, and then something like store the contents of register, yeah, let's say it's in some offset, let's say percent %sp R1. We are not using percent, yeah, whatever. So you understand that is you want to store the contents of register R1 in some some memory location. So if you see the value that is produced by this instruction, the value that is produced by this instruction, it will, we are using it, it acts as a source operand here. But what happens is multiply instruction can take some 30 clock cycles in the processor. And so the store instruction has to wait till the multiply instruction is finished. So what we can do is, if there are instructions after store instruction, like for example, add R12, R10, R15, and some instructions like that, and these instructions they don't access the memory location associated with this with the variable x, then what we can do is we can move these instructions before the store instruction. Then what happens is, by the time the processor hits the store instruction, the data that is present, that the value produced by the multiply instruction is available in register R1, and store can successfully be initiated without inducing the processor to any, without putting the processor in a wait state. So this is a very basic introduction to instruction scheduling. That is, we kind of move instructions around uh, without changing the semantics of the program, or rather, uh, as we prevent the semantics of the program, but we move the instructions around so that the number of stall cycles uh, induced gets minimized. And this is the job of the instruction scheduling module. Okay, so the goal of this is schedule instructions, optimize, minimize stall cycles, CPU stall cycles, by moving instructions around without changing the semantics of the program. And if you see the register allocation module, so that's what we will be focusing on. So there are k registers that are available. And the goal is, as I said, we want to minimize the main memory traffic. And further, of course, we would like our algorithm to run in linear time or max quadratic time, but not exponential time. So that is the goal. Come up with but that it turns out that the optimal register allocation algorithm, it's an NP complete problem. And so you cannot hope to get an optimal register allocation, but we can use suitable heuristics, which does a very good job in practice. So first we will see, in today's class, we will see register allocation for straight line sequence of code, that is register allocation within a basic block. So that is the reason. So this is what is called as a local register allocation. So local register allocation, because we are working within basic blocks, where within a basic block, the code is a straight line sequence of code. So as I said, so out of the K machine registers, we separate or reserve some F machine registers. And those F machine registers like include special purpose registers like stack pointer, base pointer. And there we need some registers to handle computations involving variables which cannot be promoted to registers. And we need registers to handle spill code. Usually the registers to handle spill code and the registers to handle computations involving variables which cannot be promoted to registers, we can reuse them. Okay, so the same set of registers can be used to handle this case and this case usually. And the first algorithm that we are going to see is a very simple algorithm. So we look at the basic block and we look at various virtual registers that are present in the basic block, and we compute the frequency with which different virtual registers are used, and we prioritize them. Okay, so that is a virtual register which is used the most number of times. We should assign it a priority to assign a physical register to it. So in essence, let's say if you are using n virtual registers, and we kind of order them in the decreasing order of frequency of usage, and for the top k minus f virtual registers, we assign physical registers. And once we assign physical registers, we have to generate code or modify the code to reflect this mapping of virtual registers to physical registers. This is an extremely simple algorithm. We'll try to understand this by taking a look at this example. So on the first column, what you have is a code with a sequence of 3 address tuples. And on the second column, we have the associated assembly code. And you can see variable X, the virtual registers allocated to different variables. And I would also like you to make a note that or here, for example, when we are accessing X for the first time, we are promoting variable X from the memory to the virtual register VR1. But here on this is where promotion of variable X to VR1 is happening. But when we are using X for the second time, we are just using VR1 as it is. We don't need to do that promotion again. This is how the whole thing is set up. And let's assume that the available physical registers for allocation are 4. There are 4 registers available for allocation. And this is the frequency with which different virtual registers are accessed in this sequence of code. VR1 is used 4 times, VR2 is used 4 times, VR3 is used 2 times, so on and so forth. So, and our algorithm or approach is very simple. So we have 4 registers available, and these are the 4 registers which are topping the chart. Of course, there is some kind of what do I say, tie between VR4, VR5, VR6. We have arbitrarily resolved it by saying VR4 gets the physical register. And you can see the register assignment here. So X is assigned physical register R1, Y is assigned physical register R2, T1 is assigned physical register R3, Z is assigned physical register R4, and there are 2 registers R5 and R6 are used to handle handle spill code. So we'll see what is a spill code in a moment. So if you see this instruction since variable X is allocated register R1, so this instruction got transformed to this. Wherever VR1 is there, we replace it with R1. Similarly, here VR2 is assigned R2. So X is promoted to physical register R1, Y is promoted to physical register R2. And then T1 is allocated virtual register, physical register R3. So what happens is we map this instruction to this instruction with all physical registers. Subtract R3, R1, R2. Because VR3 is allocated the physical register R3. Similarly, here on VR4 is allocated R4. So this load instruction gets mapped to this. And here is an interesting case. So VR5 is allocated, VR5, virtual register VR5 is associated with the variable T2, is associated with variable T2. But VR5 is not allocated any physical register. So what we do is we compute the value, the product of R4 and R3, and store it in the scratchpad register R5. And the contents of the scratchpad register R5 is stored in the memory location associated with variable T2. And this instruction which spills data that is generated or the values that are generated in the scratchpad register in the processor to the memory, that's called as spill code. So this is spill code. Similarly, here if you see VR1 is mapped to R1, VR2 is mapped to R2, VR6 is associated with variable T3, but VR6 is not allocated any physical register. So what we do is we add R1 and R2 and store it in the scratchpad register R5 and store the contents of register R5 into the memory location associated with the variable T3. Similarly, this is another interesting instruction. So we want to multiply VR7 and VR6 and store it in VR8. So VR7 is the value associated, that constant value 20. So we load 20 into scratchpad register R5 and we store VR6, that is T3, with the memory associated with so we load from VR6 is associated with variable T3. So what we do here is, so we load the contents of variable T3 into R6, which is yet another scratchpad register. We multiply them and store it in register R5. The contents of R5 is stored in the memory location associated with the VR, which is T4. That's it. So this is how we can map our virtual registers to physical registers. So the first phase is the mapping phase, and we can use some algorithm to map the virtual registers to physical registers. But after the virtual registers are mapped to physical registers, we have to rewrite the code so that all these virtual registers in the second column, they are replaced with suitable physical registers. Not only that, the appropriate spill code is also generated in this process. And this spill code is bad for us because spill code means we are going and accessing the memory. Either it is for store or it is for load. And our goal in the register allocation algorithm is to minimize the number of main memory accesses, or put it in another way, we want to minimize the number of read instructions that we are seeing on the screen. Okay, because spill code implies memory accesses, so we want to minimize the number of read instructions, or the instructions which are coded in red color, we want to minimize it. So now the question is, so what if the code is not straight line sequence of code? That is, in general, all programs, they are not straight line sequence of code. So, but in any case, we restricted our attention to basic block, and basic block contains straight line sequence of code. So this algorithmic approach that we have seen within a basic block, it cannot quite be lifted up to control flow graph level. But we can use it within a basic block. But even if you use it in a basic block, we have to be careful, because what happens, let's say, in this basic block, there is a variable x. The variable x is allocated register R1 here, and we are using the variable x again here in this basic block. So if you don't take care of if there is no epilogue code in this basic block, we kind of get into trouble, because when we are accessing variable x in this basic block, if you go and check the main memory associated with x, then it's a problem, right? Because the main memory associated with x, it may not contain the latest value associated with x. So what we do is at the end of this basic block, in order to patch up things, and also, like for example, this could be another basic block. And when we do register allocation, there can be another basic block here. There can be three successors to this basic block. So things can get tricky, because in this, let's say, the register allocation algorithm, the local register allocation algorithm, in this basic block may decide to keep this variable x in the memory only. That is, it doesn't want to promote it to a register, because there are other better variables which can be placed in registers. And in this basic block, the register allocation algorithm may think it's a good idea to promote it variable x to register, but it may not allocate register R1, it may allocate some other register R2. Similarly, here, it may allocate some other register R3. So all these are possibilities. And the simplest way to patch up, although it's inefficient, is at the end of this basic block, you just have a store instruction. So you store the contents of register R1 into the memory location associated with X, So that way, so the register allocation algorithm can kind of work independently when it is processing one basic block at a time. Needless to say, this is a very bad approach, because there could be lots of inefficiencies. So for example, if you have something like this, if you have a uh, loop like this, then you are doing lots of computations here. You store the variable x in the memory. You go back to the beginning of the basic block. You load the contents of variable x into a register again, and this keeps going on. So you end up generating lots of unnecessary main memory accesses. So we have to go for global register allocation algorithms, where register allocation happens at the granularity of a control flow graph. We will not study global register allocation algorithm in today's class, but in the next week's class, we will study how to do global register allocation. That is register allocation at the granularity of a control flow graph. So some of you might be already be thinking, yeah, it's okay even if we restrict ourselves to local register allocation algorithms. The top-down register allocation doesn't look quite right. Right? So the problem in the top-down register allocation is, let's say, if you have a basic block, in this basic block, let's say there are some virtual registers which are actively used in the first half. So in the first half of the basic block, let's say virtual registers VR1 and VR4 are heavily used. And in the second half of this is a basic block. In the second half of the basic block, let's say virtual registers VR4 to VR8 are heavily used. But what we do is we are allocating virtual registers, physical registers to virtual registers for the whole basic block level granularity. That is, once VR1 is allocated, let's say register R1, even in the second half when VR1 is not really used, the R1 register is still bound to VR1. So we are not able to reuse it, for example, let's say for virtual register VR8. So R1 is tied to virtual register VR1, and in the second half, when VR1 is not heavily used, but VR8 is heavily used, we are not able to reallocate the physical register R1 to the virtual register VR8. So this is a problem. So how do we solve this problem? So there is this algorithm called as bottom-up register allocation algorithm. Let's see how that algorithm works. I'll use a whiteboard to explain this. So what we have is we have a sequence of instructions. So this is our basic block. So we have a sequence of instructions. So let's say, so we have add instruction, we have a subtract instruction, add again, add again, add again, like that. So the way the bottom-up register allocation algorithm works is, so you start with the register. Let's say you start with uh, the instruction add, and what we try to do is we see and then we maintain so a free pool of registers. Initially, let's say we have registers R1, R2, R3, R4 available. We have these 4 physical registers available. So what we do is we take one instruction at a time. Let's say the instruction here is VR1, VR2, uh, VR3. Let me draw this pool here. So here, this is the free pool R1, R2, R3, R4. So let's say this is the status here. So when we are processing, or rather, let me use this. So these are the registers at this point in time. At this point in time, this is the free pool of registers. So when we are accessing VR1, VR2, VR3, so you see, we note that these registers, they need to be mapped to physical registers. And so you go look at the free pool of registers. Yeah, there are free registers available. So what we do is we allocate each of them a physical register. So we say add R1, R2, R3, and then we maintain a table. The table can be something like, so VR1 is allocated R1, VR2 is allocated R2, VR3 is allocated R3. This is the current table. This is the current table of uh, table which maps virtual registers to physical registers. So let's say we have something like now we are 4, we are 5, and we are 1. So now when we try to look at this instruction, that VR1 is already allocated register R1, so it's not a problem. We just say VR1 is allocated R1. But if you look at VR5, VR5 is not allocated any register. So we want, so what we do is we go and look at the free pool of registers, and we know that R1, R2, R3, they are already allocated, and R4 is available. So what we can do is, we say VR4 is allocated register, sorry, VR5 is allocated. Yeah, so VR5 is allocated uh, register R4, no problem. But when we come to VR4, so virtual register VR4, so now when we go and check the free pool of registers, there is no free pool of registers available. So it's a problem. We cannot allocate a free pool of registers. So there are two ways of looking at it. So there is one way of solving this problem is we say VR4, it doesn't, uh, so VR4, it will not be allocated any physical register, but instead we kind of use the scratchpad register R5. Okay, you store the contents of this result in scratchpad register R5, and then you generate spill code. So what does the spill code do? Spill code stores the contents of register R5 into the memory location associated with. Let me use a shorthand for I use VR at VR4 to indicate uh, that VR4, the memory location associated with the VR4. Like for example, VR4 is allocated with a compiler temporary variable T1, then what it means is store the contents of R5 in the memory location associated with T1. Maybe I will just use this for the sake of simplicity. Okay, I'm just using T4, but T4 gets translated into equivalent register, equivalent addressing mechanism, memory addressing mechanism. So this is spill code. This is spill code. This is one way of handling it. But then it may so happen, like register variable T1 is used quite a bit. And like, for example, registers R2 and R3, which are associated with some program variables, let's say they are associated with X and Y, they are not at all used down the lane in the basic block. So instead of taking this approach where we are spilling the contents of variable T1 to memory, what we can do is we can use an alternate approach. Okay, we can use an alternate approach. What is the alternate approach? The alternate approach is you try to find the variable or the virtual register which is used farthest in the future. Find a register which is used, find a virtual register which is used farthest in the future. Like, for example, let's say here the code is looking like this. Okay, so you use, for the sake of simplicity, okay, I use VR6, VR2, VR3, maybe VR5, VR4, VR2, like that. So now what we can say is the variable which is used farthest in the future, if you see the next instruction add or the instruction add after this instruction, the virtual register VR1 is not used at all. So if you think about it, VR1 is used at infinity point in time, okay, in space or down the lane. So the best instruction, if you use this, apply this rule, that is find a virtual register which is used farthest in the future, then VR1 is the register which is used farthest in the future. So what we can do is we can reallocate the register with the R1 that is associated with VR1, and we can assign it to VR4. So what we want to do is we want to reassign R1 to uh, R1 to VR4. This is what we would like to do. Earlier, R1 is allocated to virtual register VR1. Now we want to allocate R1 to virtual register VR4. So that is the decision that we took. And how do we implement that decision? The way we implement, if you would like to implement that decision, so that is here in this place of R5, that is what we would like is, so here, so what we would like is, we would like to use R1 because we want to reallocate register R1 to virtual register VR4. But if you use it as it is, we get into trouble because R1 at this point in time, it is holding the value associated with the memory location X. So we have to insert instruction, a store instruction here, store in memory location associated with X, uh, the contents of register R1. This is the spill code. The spill code here is looking green. So we add a spill code here that is store the contents of register R1 into the memory location associated with X and reuse the register R1 and allocate it to virtual register VR4. That's what we do. So in general, in this particular case, VR1 is not occurring in the text at all, but it could be the case VR1 is occurring, but it is occurring, let's say, in the last instruction, okay? Because we are kind of looking at the instruction which is used farthest in the future, and we decide to spill that particular virtual register. So the idea is very simple. If there are free registers available, you use those free registers for allocating, for mapping them to virtual registers. But if there are no free registers available, pick a virtual register which is used farthest in the future and spill it to the memory and reuse that register and map it to the current virtual register, which is demanding for a physical register. That's the idea. It so turns out that such a simple strategy is, we can kind of argue about it optimality uh, if the code is a straight line sequence of code. If you are working at within a basic block level, apparently it's very optimal approach. And it kind of makes sense if you want to draw an analogy with some ideas which you have already learned in some other class. Like in the operating systems course, you keep generating memory accesses, right? So memory access A1, A2, A3, and these memory accesses, so if you want to, we can map these memory accesses. Let's say these are all memory accesses, and these memory accesses, we can map them to page accesses. That is page 1, some page 2, because every memory is falls in some virtual page, P1, P2, P3, P4, so on and so forth. Uh, and so when we access a particular virtual page, and if it doesn't contain a physical memory page, then if there is a free physical page available, we are talking in the context of operating system now, then what we do is we allocate a that virtual page a free page, right? So you recall the discussion from your OS that this is your physical memory and this is your virtual memory. This is your physical memory. This is your physical memory. This is virtual memory for one process 1, virtual memory for another process 2. So a page here could be mapped to some page here. A page here could be mapped to some page here. So let's say when a process that is sitting in this with the process P2, when it is executing, let's say if it accesses a virtual page and that virtual page doesn't have an associated physical page, and if a physical page is available, then a physical page can be allocated to that virtual page. But on the contrary, if all the physical pages are allocated to some virtual page or other virtual page, the optimal, then a page replacement algorithm kicks in. So we use different page replacement algorithms such as first in, first out, least recently used, things like that. But the optimal page replacement algorithm, the optimal page replacement algorithm, so what is the optimal page replacement algorithm? Pick or evict a page which is used, evict a page which is accessed farthest in the future. This is the optimal page replacement algorithm. That is, a page replacement algorithm which minimizes the number of page faults is pick a page which is used farthest in the future. But in the context of operating system, virtual memory, in this case, we don't know, we cannot predict the future. We don't know which page is going to be used, which is going to be accessed farthest in the future. This information, that is the page which is going to be accessed farthest in the future, this information is not available to us. So what do? We kind of approximate this by looking at the past, that is least recently used algorithm or LRU, FIFO. These are all approximations to this optimal strategy, because LRU and FIFO, so we can find this out by looking at the past. But whereas this policy, we cannot implement this policy. So we use LRU, FIFO, and other schemes to approximate this strategy. And it also, we know that LRU is a two approximation of optimal. It's a two approximation. That is the number of page faults generated using LRU. It is half. It is within 2 times the optimal. It's a two approximation, LRU. So why are we telling this story? Is in the context of OS, we cannot look at the future, so we approximate it by the past. But in the context of compilers, in the context of local register allocation algorithm within a basic block, it is possible for us to see the future because this is space. You just go look into further down to figure out, you can just go look further down to figure out what is the virtual register which is used farthest in the future. The problem which we face in the context of virtual memory, we don't face that problem in the context of uh, register allocation within a basic block using this particular strategy, that is find a virtual register which is used farthest in the future, spill it. Spilling is nothing but evicting that the variable which is sitting in that virtual register and associated physical register. So this is the main idea. This is an extremely cool algorithm and nice thing to actually implement it in LLVM if you are trying to get your hands dirty and see how LLVM works, for example. So finally, I would like to, maybe I will take this up in the next class, but let's see. Yeah, I think I will stop here. So there is one more idea on how to do local register allocation using graph coloring, but we will take up this approach. It's a very, very interesting approach. We will take this approach in the next class. So I will conclude today's lecture here. And the particular register allocation algorithm that we have seen, this is what is called as a bottom-up register allocation algorithm. So that's all I have for you today. Thank you and have a great weekend.
Hello, sir.
Yes. Yeah.
Yeah, am I audible?
Yeah, you're audible.
Yes, sir. So actually, I wanted to ask how should we proceed with the next phase of the project?
I posted all the information, Apurva. I cannot know your all the homeworks, everything is geared to that. So if you see, I posted a in the homework one reading exercise on
Yeah, right.
yeah. So you do read all those things, and you should. That's the way to go. So
Okay, sir. Okay,
yeah,
sir.
okay.
Thank you.
Yeah, regarding projects, so it's very important that you get started early and do things, and all the necessary resources are posted. Please go ahead and work on. Okay, so that's all.